So the term nuclear charge just refers to how much positive charge is in the nucleus. What's the charge of the nucleus? Nuclear charge is the charge of the nucleus. So if I just said, what's the nuclear charge of cadmium? You'd find cadmium, and you'd find that it has 48 protons. So its nuclear charge is 48 plus charges. The effective nuclear charge is how much of that positive charge is experienced by the valence electrons. The valence electrons only feel part of that positive charge attracting them. Right? So it's like, you have two magnets and they're stuck together, they're right next to one another, they feel a full attraction to one another. If you pull them away a little bit, if you pull them enough away, they don't feel any attraction. So the attraction now between the magnets is zero. So the effective charge is, in a practical sense, how much of an attraction is there actually? So for cadmium with 48 positives, to get the effective nuclear charge, I have to recognize that some of that positive is going to be canceled by all the inner core electrons and their negative charges repelling the valence electrons and pushing them away. And so, yes?
When you explained it, you said that it's like the valence electrons, but on there it says by an electron in atoms, so I'm just
Right. So when you see a number for effective nuclear charge, usually that refers to the valence electrons, because the core electrons usually experience enough of a charge attraction that they're not going to be undergoing any changing. But you could still talk about the effective nuclear charge of one of the core electrons. If it's not specified, you probably would assume that it's for the valence electron. But the core electrons have a much greater effective nuclear charge. If you think about cadmium's core electrons, so cadmium's outer electrons are in the fifth energy level, so its core electrons are the first, second, third, and fourth energy level. But cadmium's 1s electrons, they're right next to the nucleus, so they experience the full 48 plus charge because all the electrons are outside of that and they're not interfering with that attraction. So you can still talk about the effective nuclear charge of the inner electrons.
So how do you get the number? Do you subtract from the number?
So the number is something that I think is determined experimentally. So there's no, that I'm aware of, there's no formula that you necessarily use.
So
I wouldn't ask you to calculate the number.
Okay, I would just explain what
Yeah, explain what it is, maybe compare two elements qualitatively or relative to one another, which element 2s electrons experience a greater effective nuclear charge or something like that. So the size of the element is determined by the same factors that affect the effective nuclear charge. And that is shielding and how much positive charge is in the nucleus. And you can see by this chart, which shows relative sizes, these are obviously not to scale. They're much smaller than this, but it shows the relative sizes. So some of these are much larger than others. And that has to do with how much positive charge there is versus how much shielding there is. So which is a bigger factor in determining size? The quantity of shielding or how many protons there are in the nucleus? Shielding, is that evidenced by the table? Well, we already said shielding is the bigger factor, but does that match up with the way that the trends in size are on the table? As I compare elements that are in the same horizontal row, how does the shielding change from one element to the next? Is there a big difference in shielding between carbon and fluorine? How do I determine shielding? Yeah, find out how many core electrons there are. So elements in the same row have the same number of core electrons. Carbon's valence electrons are in the second energy level. Fluorine's valence electrons are in the second energy level. So their core electrons are just the first energy level. Carbon's core electrons are 1s2. Fluorine's core electrons are 1s2. So they have really similar amounts of shielding. Fluorine does have 3 more electrons total than carbon, and the valence electrons do shield one another a little bit. Right? So with fluorine's 7 electrons in the second energy level, they do repel one another a little bit. And carbon only has 4 electrons in that level, so they will repel a little bit less. So ultimately, the more electrons I have, the more repulsion between them, the more shielding. But what we're focusing on is how many core electrons there are, because they do the vast majority of the shielding. So when I have 2 elements, like carbon and fluorine, they're in the same row, and they have the same number of core electrons, they should have similar amounts of shielding. And so if I look at one of these rows, the sizes are different, but they're not dramatically different. Because the shielding is the bigger factor, and there's not a big difference in shielding. How do I explain why fluorine is smaller than carbon, even though it's just slightly smaller? How do I explain why is fluorine smaller than carbon? Right. It has more protons. So when 2 elements have similar amounts of shielding, they should have similar sizes. Then, to determine which will be slightly smaller than the other, I need to look at which has more protons. So if there's more positive in the nucleus, it will attract the electrons a little bit closer. All of the energy levels, energy level 1 and 2 for fluorine, are a little bit closer to fluorine's nucleus than energy levels 1 and 2 are for carbon, because fluorine has more protons to pull those levels closer, pull the electrons in those levels closer. If I look as I go down, now I see big differences between the smallest elements at the top and these really large elements at the bottom. The elements at the bottom are really big, comparatively, because they have a lot more shielding. Right? So when I go down the column, I see much more dramatic changes in size, because when I go down a column, that's where I'm really changing the amount of shielding. So if I go from, like nitrogen down to bismuth, the example we talked about earlier, as we said with bismuth, its valence electrons are in the 6th level. So it has 1, 2, 3, 4, 5. 5 core levels. That's a ton of electrons shielding the outer electrons of bismuth. They're going to be really far away from its nucleus. Right? So if I give you any 2 atoms, and I ask you to compare their sizes, those are the 2 factors you consider. The shielding first, and then the number of protons. So let's look at a couple examples here. So we've got 3 elements here. We want to rank them in order of atomic radius, maybe from smallest to biggest. So of those 3, phosphorus, sulfur, oxygen, we find them on the periodic table right here. Which one should be the smallest? Yes. The oxygen should be smallest, because oxygen has 2 core electrons. Very little shielding. Shielding is the major factor. Then, when we look at phosphorus and sulfur, just looking at phosphorus for a moment, it has 1s2, 2s2, 2p6, 3s2, 3p3. Phosphorus's core electrons are in the 1st and 2nd energy level. 10 core electrons doing the majority of the shielding. That's a lot more than 2 core electrons doing the majority of the shielding. So it's going to be bigger. If I compare that with sulfur, which is right next to it, the sulfur would have 4 electrons in the 3p instead of 3. Still the same number of core electrons. So similar amounts of shielding between sulfur and phosphorus. We can't really use that to distinguish between them. Then we go to the number of protons. So between sulfur and phosphorus, which should be smaller? Sulfur. With similar amounts of shielding, the one with more protons will attract the electrons closer. It will be the one that's smaller. So sulfur should be smaller and then phosphorus. Which has more shielding? Sulfur or phosphorus? They're similar, but they're not exactly the same, right? Because phosphorus only has phosphorus has a total of 5 valence electrons. Sulfur has a total of 6 valence electrons. So with one extra electron, that one extra electron in the third energy level will repel the other electrons in the third energy a little bit and force them all slightly further out. So there's slightly more shielding. In any element that has more electrons, it will have at least somewhat more shielding, a little bit more shielding. But since the core electrons do the majority of the shielding, that slight additional shielding that sulfur has that phosphorus doesn't have is not going to be a big factor in determining size. So once we determine they have the same number of core electrons, then we use the number of protons to determine which should be larger. Okay, looking at 4.14. In the periodic table, the element hydrogen is sometimes grouped with the alkali metals and sometimes with the halogens. So, as we talked about before, hydrogen, we talked about helium, but hydrogen in this particular question is saying that hydrogen is here in column 1, so it's similar in properties to these elements, but it also has some similar properties to the elements in 7. Why is that? Because it's one away from a noble gas. So what do these elements all have in common? If they were to gain 1 electron, they'd make the same number as a noble gas configuration. That would be good. It makes it a little bit more stable. And hydrogen can do the same thing. If hydrogen gains 1 electron, it'll make the same number as helium. So it's relatively good at holding on to its electron. But as far as its electron configuration, it has the same number of valence electrons as the other elements in group 1A, so that's why we put it in that column. So just wanted to point that out. 4.20. Maybe we'll just do one of these. 4.20. So maybe we'll look at A. What element are we talking about here? NS2, N-1, D8. What does this type of notation mean? What is N? Yeah, it's the energy level or principal quantum number. So this type of notation, all they're saying is I could substitute any number in for N. Right? N, the principal quantum number, tells me the energy level. Could be N equals 1, 2, 3, 4, etc. With this type of configuration, what's the minimum value that I could have for N? Can N be equal to 1 here? Not in this case, because there's no 1 minus 1. Right, so what's the first level where I actually have a D show up? The third energy level. So the minimum number for N here, it's got to be equal to or greater than 4. Because I have to have 4s2 and then 4 minus 1, which is 3, d8. So this type of notation could be 4s2, 3d8, or a 5s2, 4d8, or a 6s2, 5d8. Those elements that we're talking about are these ones: nickel, palladium, platinum. They have 2 electrons in an s, and 1, 2, 3, 4, 5, 6, 7, 8 electrons in the G. Right, so if you see that notation, you should be able to determine That notation just tells you which column you're looking at. It doesn't tell you which element in the column. It could be any of the elements in that column. I'm not going to probably use that notation much, but you should at least be somewhat familiar with it. 4.30, why is the radius of the lithium atom larger than hydrogen? So lithium and hydrogen have the same number of valence electrons, one valence electron. Why is lithium so much larger? And if we go back here, we can see that. Huge difference in size between hydrogen and lithium. What's the reason for that? Right, hydrogen doesn't have any shielding. It's just one electron. That one electron feels the full attraction to the nucleus. Lithium has 3 electrons. 2 are in the first energy level. Those are the core electrons. They do the majority of the shielding. The valence electrons in the second energy level, so it's really repelled by those core electrons, so it doesn't experience nearly as much of an attraction. So that's just one example to illustrate how important shielding is, and the big difference in size there resulting from that difference in shielding. So 4.44, maybe we'll just, so we did one of these, maybe we'll just do one more. So let's look at D. 4.44D, we're comparing chlorine versus iodine. And this one is relevant to the lab that we're going to start today. So if I had to determine the difference in size between chlorine and iodine, which of those two should be larger? Right. So this is the other point about the quiz I was wanting to mention, I forgot. It's not adequate if I ask you to explain the difference in size or the difference in ionization energy or electron affinity. It's not adequate for you to say iodine is bigger than chlorine because it's lower on the periodic table, or this element has a higher electron affinity because it's further to the right on the periodic table, and the trend is that as you go to the right and the top, the ionization energy increases. Okay? That's just a trend. That's just an observation. That doesn't explain why. If I want you to explain why, you've got to talk about shielding, number of protons, full or half full energy levels, having the same number of electrons as the noble gas, possibly if that comes into play. For size, there's only 2 factors, shielding and number of protons. So if I want you to explain why chlorine and iodine have the difference, those are the 2 factors you mentioned. So for chlorine, since shielding is a bigger factor, its valence level is the 3rd level. It's shielded by the first 2 levels. For iodine, its valence level is the 5th level. Those valence electrons are shielded by the first 4 core levels. That's a lot more shielding. So even though iodine has a lot more positive charge in its nucleus to attract electrons than chlorine does, all that extra shielding is going to make iodine significantly larger. So since shielding is a bigger factor, you go with that factor if there's a big difference in shielding, and there is in this case. So iodine is going to be larger, mostly due to the shielding, and I would expect you to have a few sentences on that on your exam if I ask you to explain the difference there.